The plasma frequency is the most fundamental timescale in plasma physics, and there exists a distinct plasma frequency for each species, with the electron plasma frequency being the most crucial. When textbooks refer to the plasma frequency, they typically mean the electron plasma frequency. This frequency corresponds to the electrostatic oscillation frequency of a species in response to a slight charge separation. Consider a one-dimensional scenario where a slab, comprised entirely of particles of a specific species with charge and mass, is displaced from its quasi-neutral position by a minute distance parallel to the axis. The resulting charge density on the leading face is countered by an equal and opposite charge density on the opposite face, generating an electric field within the slab. Fitzpatrick, 2008. Applying Newton's second law to an individual particle within the slab results in plasma oscillations, observable when the plasma system is studied over time periods longer than the plasma, and external influences modify the system at a rate no faster than described by equation 1.6. Studying phenomena faster than this implies the investigation of non-plasma physics, such as nuclear reactions. Observations over length scales shorter than the distance traveled by a typical plasma particle during a plasma period will not detect plasma behavior. This spatial scale, equivalent to the Debye length, equation 1.7, is defined by equation 1.8, independent of mass and generally comparable for different species. Our idealized system can effectively be considered a plasma only if the conditions outlined in equations 1.9 and 1.10 are satisfied, where τ and L represent the typical timescale and length scale of the process under investigation. Despite the conventional requirement of equation 1.9, plasma physics demonstrates the capability to describe structures on the device scale, as exemplified by the theory of the Langmuir sheath, a boundary layer surrounding a plasma confined by a material surface. Hazeltine and Weilbrook, 2004, Lieberman and Lichtenberg, 2005.